one back, please. Okay. Right, I did that together with a new fellow. And what is it about? I start with this from my friend Felix, which is the yearly view of the activity. That's manual counts of a beacon. The scale is something like 80. Some of the bigger quantities are in saturation, otherwise you don't see the detail on the lower one. What you see for the, what's that? Quadrantics, one day, very sharp and very strong. March, February, March, oh, almost nothing, sporadics. April, lyrids. May, at aquarids, something picking up. In June, you have the highest activity of all year during the daytime. So we don't have that in the southern hemisphere. They have some of that. This is long-lasting and the strongest and the longest stream of the year. That was detected, of course, by radar and confirmed here. July, we have some streams, Perseids, of course. Perseids are a bit complex because they're long-lasting. There are secondary peaks. The radians with us are in the zenith. Okay, this. What else? October, Orionids. Where are the Leonids in November? Almost not visible. Sometimes they have low activity and the speed is high, and there is something due to which the visibility or the observability also decreases the ceiling height. I'm not explaining that. It means that the optimal speed for our kind of thing, is like the ones of the Geminids here in December. That's the nicest of all. So the speed of 35, 40 kilometers per second is optimal for the things we are doing at 50 megahertz and some others. That's a fact that's there. So this is pretty universal. It changes, of course, from year to year when they have an outburst or a stream which is more active. But the general picture, I believe, is really good. So the main shower is indicated, and there is a sporadic background. That's the time we normally do nothing. I mentioned that, September. Right. The two beacons, you have already heard enough about that. Here you have Durbe. We call it Durbe. That's the Brahms one. And then we have called Yper there, which is the VVS one. And Johan is located here. And we are here a bit north, I believe, somewhere there currently, 100 kilometers north of it. Right. There is the receiver. So Durbe is southwest 90 kilometers, and Yper is straight west 160. Okay. We have mentioned that too, 50 watts on that frequency. And here we have the guys. Johan is here to the left. Sorry. Oops. All right. That's Johan to the left. This is located near the public observatory. You might say, hey, is that not blocking some of the view? Maybe, yes, but it is pointing upward and it's blocking horizontally some of the stray radiation anyhow. It exists for 20 years, it works, so it's not the biggest problem of all. Right. Beacon Durbe, like I said, is 400 watt. I just read 350, more or less. So there it is. And Johan did the following. He has one antenna. That's a big thing in 3 meters. Due west, 70 degrees elevation. He used a dual receiver, a good quality dual receiver, but he uses only one channel, contrary to what you might think. That's no problem, of course. The signals are 20 kilohertz apart. The bandwidth of that receiver is enormous, and the sensitivity is exactly the same. And it's the software that separates the two channels. This is very common by now with software-defined radios. You can do that. So the elements are, and then of course, once you have your two channels, you feed that in two instances of a Meteor detection program. Here we are. This one is called Radio Meteor Detector by Jean-Claude Thibault. This is getting more and more popularity. It is getting better in the sense that you have true detections and less mistakes. And it's also getting very fancy with the console and real-time things and tuning things, but you should stay off of that when you want to do scientific observations. So this works, and let's see what we have. So repeating the complete chain, we have the transmitters, more than one. We have the local conditions, maybe it's humid, there's something else going on. You have the atmospheric, I mean, the upper atmospheric things. You have the meteor themselves, you have back to the ground, and you have the local transmitter. So it's a big chain, and you have the receiver and then the detection probe. So it's a long chain where something can go wrong. And here, at least with that one antenna and one receiver, we skip out some of the part of it. Johan got in December of last year, so it's very recent, got excellent results with the Geminids, as well as in January with the quadrantids only for one day and some gaps. So we can be pretty confident that there he has a good setup and a stable setup. Now turning to March, where there is only sporadic activity, probably. Let's see that. We have the two Durbe Ypres below. The quantities vary between 66 and 32. You say the number of Durbe is only double of the one of Ypres, and the power is 7 times higher. Is that correct? Yes, because it's not a linear scaling. I must also add that the sensitivity for Ypres was a bit put up. So there is no direct comparison possible. It's not claiming anything there, and also definitely not doubting that the output of the transmitters is correct. Okay, why would it then be? I think it's mainly because of our time resolution that the very short ones are not captured for the ones of Durbe are not captured in that setup. So you see the daily pattern arriving at that. Of course, we know it's higher at midnight. There are no showers. There's nothing to be seen. And is it really constant during the month, right? Okay, some simple statistics. Just the daily mean for Durbe and for Ypres. I put them on purpose on the full scale because otherwise you might think this trend is much too bigger than it is. It is not. There is a small trend during the month for both of them, not identical. My conclusion from that is that so the arrow bounds, so I say that the 1 sigma arrow bounds are there, and basically everything falls in this. You have no positive outliers. A positive outlier would mean an interference or a shower. It's not there. And you have no negative ones due to an interruption or something like that. So it's quite almost a complete stable thing. Right? This is the same thing set out during maximum of extreme is at 6 in the morning local time. We have to here account for that. The midterm interval is half an hour, and it's 5 degrees to the east is another 20 minutes. So we have to shift by 1.8 hour. Here we see some, I think, still spectacular things. The difference between the maximum and the minimum in both cases is a factor of 5. In visual work, I don't think you hardly see that for sporadics, but here we have the whole day. We have to take benefit of our thing. Like I said, this is local time, what we do. Now, during the day, let's do a test if these are randomly distributed, Poisson distributed. And yes, with some goodwill, they are. The distribution there says there's a little bit much in the tail. That's because in the beginning of the month, we have some lower ones, and the end of the month, some bigger ones. It's not completely correct, but you can repeat that 2 times, 24 times hours, and it passes the test. But okay, right, said that. Okay, let's now do correlate them, the daily one for Ypres and the daily one for Durbe. And this is what comes out R square of 90%. Not bad, going through the minimum. But when I connect the points, they exhibit this thing. They are not really randomly, there's a kind of ellipsoid. And that reminds me about this. The not so young ones amongst us will know this. This is an oscilloscope. Weird comparison maybe. And also this exists today in handheld. It's a computer. What does that thing do? It displays really a time signal horizontally, but you can put also the signal horizontally and vertically, and then you get Lissajous figures that vary with phase. When I do that and I try a shift, then let's see that this is what we have. One shift to that direction, oops, that's the wrong way. This one is much better, and another one is too far. And the correlation there clearly goes through a minimum with a shift of 1 hour. I have no idea why this is. It's not a mistake. It's not a silly time mistake of a time zone or something like that, but I cannot tie that out with the correlation between the directions. But it's certainly something unexpected, and I want to continue with that. I modeled also the sporadic background up to the third harmonic, and there you see the same thing happening. It fits well. The sign is the main one, but with having some harmonics, the time between the maximum and the minimum has not to be 12 hours. I'm skipped quickly through that one. Stein showed that already, the double exponential model with a sign error corrected that SIS found out recently. Also, Johan there has, these are the results from Johan. And also, like Stein said, we have here like 51 unknowns, 24 plus 24 plus 3 real ones. And the thing now is, you don't need 24 sporadic values. Maybe you can just do with 7, the constant plus 3 harmonics. Not a fixed amount, but also getting that. This will have an effect on the shift, on the fit. The fit will become worse because now we are not able to put any mistake in these poor sporadics because they are more constrained. And an advantage is that you could find more, for instance, more a secondary peak like in the pulsates. So, and also now maybe the dendrites can be studied in that way. So, after all, I think that's good news for the stability of our transmitters and so on. And with a few harmonics, you can model better the background. And of course, we will get in detail. And then there's another challenge for Stein if once this is written in full detail. Thank you.
Thank you, Chris, for this new mystery. Are there any questions? Yeah. I see a question from Johan.
Well, maybe a comment. So we have a poster out there where we show the sporadic regions detected by head echoes. And obviously you have a slightly different geometries, which will give forward scatter for your both legs.
Yeah.
And these diurnal variation depends on kind of what part of the sporadic source regions is highest in the sky. So maybe that would be the way to go here to see if it fits with how these sporadic source regions move across the sky and give a good forward refraction geometry.
Yeah, that was basic. The takeaway of this one depends on the, no, it's not there. No, you're absolutely right. You have to look into the direction, which are the radians, sporadic radians in that area to explain it, because it's not a simple geometry thing of 50 degrees, nothing like that. But it definitely is, and we will do that, but you need more the distribution also of the lengths to see how it gets in.
We have time for another question. Is there any question online? I don't see one. I have a question myself, Chris. So, more of a comment. So, then of course, an obvious test would be repeat the same experiment for people who do have the same azimuthal and well, geometrical setup.
Yeah.
And
this is
look at that.
Not working anymore. Is it working? That's true. And I guess also like with the Bram setup with many stations, you have big opportunities there to do something about that. Absolutely. Yeah.
Indeed. Let's thank Chris again.